Yeah, so welcome to the session about the new I/O format for OpenFOAM. We're working within the scope of ExaFOAM project at Wiki GmbH. We also work on other work packages of the ExaFOAM like dynamic load balancing or also Grand Challenge and other benchmarking. Yeah, and I'm happy to show you the current development state. But first, let me introduce you to this Coherent I/O format. So first of all, I would talk a little bit about the current bottlenecks of the current I/O format. Then the architecture of this format and the Coherent one, what we do different. Then the transport layer. So how do we manage to get data to the file system? Some words about performance, and then there will be a hands-on session where I prepared a VirtualBox image. And so here in audience, is somebody interested to follow it? I have here, if you use this thing, you can get the VirtualBox image if you have a VirtualBox. So, okay. If you want here this, I posted also at Hoover the GitHub repository, so you can download it there as well and try it out. Okay, so it's formatted strangely, but never mind. So the current parallel I/O formats, there are three alternatives. What we currently have, it's the so-called uncollated format. So that's the standard what most of you used before, I think. These are the processor directories. So if you run your case on 8 cores, you will have processor 0, processor 1 until to processor 7. So the number of files written scales with the number of cores, right? You have per processor directory your field data. Once the case is decomposed, you have another problem that if you want to change some boundary, for example, from fixed value to 0 gradient, you have to do it 8 times if you have 8 processor directories. You can also only restart from the same number of cores, right? And substantial amount of time to solution goes into decomposition, reconstruction, or redistribution of your case. There is an alternative. It's called collated format. I think it's implemented in ESI version and the OpenFOAM org version. It solves one problem with number of files. So it substantially reduces file number by aggregating your data into single processor directory, or maybe you can also split it in several ones. So this issue is solved, but for other issues, you don't have a solution there. And its performance, it's not as good. Another alternative is AdiosFOAM. It's a function object implemented by Mark Olesen from ESI. And it's basically a wrapper for the current uncollated format. So if you have this format of Adios, right, of this library, if you look inside, you will see the processor directories from OpenFOAM. So what would the ideal solution look like for me? First of all, I want to decrease time to solution, meaning start a parallel run without pre-processing, meaning no decompose path. I don't want to reconstruct for post-processing, to work with data directly. And best of all, I did a single ASCII file to alter all a boundary condition in parallel case or in serial, whatever. Then another issue on if you work with high performance computing clusters, you will run into inode limit. If you have like 60 runs on 16,000 cores, so you have 16,000 folders and even more files. Another good thing would be to, if viewing in ParaView, to load just the slice of data you want to see, and also to support lossy and lossless compression. So this is now we're achieving this slowly. So we have a working prototype, and the initial idea and architecture comes from Henrik Rusche. We do it within ExaFOAM project. Apart from Wiki, there is HLRS from Stuttgart as partner working on this. And we have a prototype implementation in FOAM Extend 4.1. So let me talk a little bit about the current format, how it does think, and then we compare it to the Coherent one. Here we see a 2D case with 6 cells, right? So the cell numbers are in black, faces are numbered in red, and points in green. Yeah, the cells are numbered by meshing algorithm, block mesh, for example. The face order is so that first we have internal faces. So if we go here, I have 0, 1, 2, 3, 4, 5, 6 internal, and then first boundary comes. So this B0 is boundary, is the first boundary. Starts with phase 7, 5 faces, and here the same for B1. It starts with 12 and it has also 5 faces. How does it look like in parallel? So first of all, you have to run a decomposer, right, to reorder your cells to have a good decomposition. Then the faces and points at the processor boundaries where you cut your geometry, these are duplicated. And you have reorder your faces again for this same order, first internal faces and then boundary faces. And as you can see here, these are base numbers for partition 0, you have partition 1. And if you highlight these different partitions, then you see there is some leftover, which is present on the both sides, right? And this is this duplication. So we have the information 2 times saved on the disk, right? So what's the recipe? The idea is to enable reading and writing the same mesh, both in serial and parallel. So from this idea, the name comes into place, the Coherent format. In other words, mesh needs to be sliceable. How do we achieve it? So what are the problems to achieve this goal? First of this is this faces list. If you look into this list, you will see that if you have some cells, not only hexaeder but a mix, right? So unstructured grid, you will have list of different lengths. So in general, this list consists of list of non-equal size. The solution here is to flatten this array. So we just write it down as a single array. But now we need to know where does in this array, where does the phase start, right? So here all the point numbers are written down, and we have an additional array which helps us with this. It's called phase starts. So it points to if I go here, for example, the line 1 as entry 2. This means that if I go to this list of phases, I have to go to line 2, and there my second phase will start, right? And so on for the other phases. Yeah. Sorry, say again. Repeat. So we made out of this list right here, we made a flat list with phases, right? So we put, unfortunately, they do not correspond to each other because it was just an example. But it would be 0, 1, 1, 2, 3, right? Hmm? Yeah. It should be 0, 1, 2, 3. And sorry? And the phase starts, the first one, so the zeroth line, right? Zero entry. We'll start with 0 position in phases. Then the next phase, the phase number 1, will start with the position number 2 in this phases list. Can you follow? The phase number 2 will start at position 4. So it's not shown here, but it's underneath of 3, right? Yeah, there's a message. Ah, okay. I'll check. I mean, we need to make it sliceable, right? So if I have a list of lists, later to this question, if we have list of lists, then I'm reading this binary block phases, right? How do I know that how do I jump to the phase number 10? How do I know I know this? I cannot just take some offset. I don't know what comes before my phase number 10. Sure. There are many solutions to this, but we decided to go. Yeah. That's the main point. You mean here the with the colors? No. It's index of the phases list. Let's. So faces is actually a list of points, right? So I've got points there. So it's like in the current format and in the Coherent format, it's the same. We have points there. Yeah. No, this information. Okay, I have to apologize that they do not coincide, these lists. Maybe we will have a look at this in the hands-on session. But this list, it's list of points. So I have point array, and in this point array, I have points 1, 2, and 4, which build this face. It's a triangle, and there can be 1, 2, and 1,000. You know, it's arbitrary. It's depending on the meshing algorithm. I think we'll look at this in the hands-on session, right? So there is another problem with the boundary faces. These are stored at the end of the face list, and again, to make it sliceable, right? So we want to jump to some part, or we just want to cut one piece of our mesh of our faces and to read it. Here we have a problem because all the boundaries are somewhere at the end, and we don't want to jump to the end of the array to get these boundary faces. We want to be in the one block, you know. That's why we came up with this approach. We changed the neighbor list. Before it included, so the neighbor list gives me a cell number, which is the neighbor of my face, right? So there is a face owner, that's the owner array, and there is a face neighbor. And previously, this neighbor list ended when we came to boundary faces, right? And the boundary faces was stored in this boundary file with the start face and end faces and so on. Now we integrate the boundary information in this neighbor list. So if we have, for example, this one is the first boundary. It just got a minus sign before. It's indicating it's a boundary. It's the first one, and then we have -2. That's a second boundary. Okay. Yeah, and there was one question here. Is this going to be implemented only for ExaFOAM, or it will become to OpenFOAM ASI? We're working on the integration to OpenFOAM ASI version and form extent as well. So this will be the two versions. Let's have a look at the Coherent format. How does it look like? So it's now we have this is our faces list, right? Yeah, let's put it like this. And this is our neighbor. It looks different, but it's the same as the example before. It's just written in different form. So let's come to advantages. How does it help me to read or write a mesh more efficiently? First thing to notice is that serial and parallel meshes are not distinguishable per se in coherent format. So they look the same. We don't have processor directors anymore. It's always at the same place. And from outside, you cannot tell that it's a mesh for parallel run. If you look here, there is I have again 2 partitions, and there is now one change from before. There are no duplications of points or faces on the second partition. They are all now on the partition 0. And here it's how we, let's say, how we read the data. Let's stick to the reading, right? How we would read it, we would make here a slice. You see, if you follow this line, then what's above this line would be read by the rank 1, and what's below this line would be read by rank 2. Now the thing is that this one is only for I/O. So at the end we use the FOAM format to compute stuff. So everything else is working as normal for the computation. We will bring it to the FOAM format. That's why we need to exchange the points. We need to exchange the face information, and this is done while the reading by sending messages between the ranks.
When you say after reading and after storing the reading my class, and do I still keep the format of that my internal faces come first and then my boundary faces come? So when I ask n internal faces and I face an eval of n internal faces, will I still get involved?
You will get the FOAM. So if you it's the FOAM. It's like it's standard. It's the same as before. No. Only if maybe you want to write something on your own which follows this format, but we try to keep the API the same, so you even don't need to care about this as well. Let's say if you want to write geometric field, you don't need to care about this. It's already done by us, so we will bring it to the right format. Yeah. Okay, I see. I see what you mean. Yeah, there will be some information missing on the procs above, and for globally shared points also for the procs below. But you will know to which processor you need to talk to get this information. Yeah.
But if it's different order, they use structure position. Then I need like line 1, line 2, line 5, line 6, line 8, line 9 to form my mesh. And either we need to store this in composition by other portions that start and end, but neutral line is this, or you need to keep on the basis. And that was it.
Okay, you of course that's a good question. Okay, you're talking about this one. So this one was run on you need to run still a decomposer to get a nice decomposition, right? Because if you run it from block mesh, you can still start your MPI run. It will be red, but the decomposition will be ugly, you know. So it will be something separated into corners. You still need a renumber method, resorting method to get a nice decomposition. Exactly. Now you can do it as a pre-processing step as we had before, but now you are more flexible. You can decompose already when you read your data, right?
Same mesh, but every time I would change one of course, we need more than one cases, we change the layout.
Without using decompose path, okay? That's an important point. So yes, of course, still you will need to run efficiently. You will need a decomposition algorithm, but you can run it on the fly, you know. And if you want to, you will need to save this decomposition, because if you want to post-process the result, right, you need the right sorting, the right ordering. Okay, so for the transport layer, so under transport layer I mean program or manager which writes the data to the file system, to the storage. So it manages the tasks of aggregation or distribution of data arrays during write or read to from storage, right? And it also manages metadata for us. Our choice is Adios 2. It's acronym for Adaptable Input-Output System. It's designed for high-performance computing. Allows partial selection from a global array, exactly what we need. It also works with compression, and yeah, it's configuration easy, and API is actually simple to use. And yeah, as you can see here, well, what does it do for us? It will bring the data to the single rank, or to 2 ranks if we want to write data to the file storage with 2 ranks. We can also set up this, and it will do it for us. So we don't need to go fine-grained to manage this our own, right? We let Adios to do this for us. Yeah. It manages this internally. So it has a metadata file, and it writes, let's say, it writes data in 2 files. If you aggregate to 2 files, then it will save the information which data is stored where in the its metadata, and it will manage it for you. Not for OpenFOAM, but from Adios side. I will show it in a second. So another alternative I just wanted to mention, it's MPI-IO. And I won't go into the details, but here, why we didn't choose this one, because of this management, right? What I just explained, we needed to do ourselves. Yeah, but maybe somewhat MPI-IO has a different paradigm. So for example, it can write binary data files into a single file directly, right? Whereas at ADOS2, it will write only continuously in blocks. So it will gather the blocks and write these blocks down. It uses ADOS2 uses MPI, but not MPI-IO. Yeah. Yeah. No, we don't use this one. So, and we did some benchmarking. What you can see here, it's not OpenFOAM. It was a proxy application. We just wanted to know how good are the which transport layers, right? And the one which FOAM uses is POSIX, right? Here, M2M means that we write all the cores, right, to all the files. So M cores, right, to M files. Each core writes its own file. Let's put it like this. Then there are different strategies for MPI-IO aggregation, and here we have ADOS2, and one FPC means one file per chassis on an HPC. I don't remember exactly how many nodes this is. Somewhat 32 nodes, my guess, and you have to multiply it by 128 cores. So it's pretty good aggregation ratio. And as you can see here, it's the IO performance is shown, and down here we have number of nodes. So POSIX has a, let's say, wide spread, right? So some files are written slowly, some are written fast, and on average, it's not it's not as good, right? Because the file system gets stressed when you write a lot of files. And what we saw that the MPI-IO and ADOS2 are on par on the performance. So we have some overhead maybe in ADOS2, but it's not as large. Okay, so how much time do I have? It's 20 somewhat minutes, right? Yeah, okay, so with the hands-on session, I won't just, what I just showed on the slides, I just want to show it you on a real case. And yeah, want to show what the advantages this current format will bring to us. Yeah, and if you have questions, ask me all the time, but you did it already, so make it bigger. I would run two maybe not so big. Is it readable? It's okay. Okay, so I have on the left hand side, it's the case set up with Coherent format, and on the right hand side, this will be the one with the ASCII. Right. So and okay. So first of all, let's look what's the mesh we're dealing with here. I will keep it small so that we can see. Yeah, so it's just 2 by 2 by 2 block mesh. We have eight cells altogether. Yeah, I will run block mesh here and just go into the polymesh folder. And what we see here is our mesh. And for example, if I go into faces, that's one what I showed before. Here we have a list of lists, and every list is 4 faces long, because these are quad faces, right? We have only hexaeder cells in this block mesh. Okay, so let's have a look. How does it look like in the Coherent format? I run. I'll check if the mesh here is the same. Yeah, it's also 2 by 2 by 2, and just run block mesh here. Let's go into the constant polymesh folder. So it looks a little bit different, right? At least if I go into faces. So as you can see here, this entry 36, it's where it looks similar. After this, it's completely different. So in the Coherent format, I have an identifier. We don't have any lists here in the ASCII file. It's an identifier which I will find in my data structure of the adios format, BP format. And we can just have a look into this one. And this we always call it data.bp. So where would you find some heavy data in the form folder? There will be now an ASCII file, which would be also there before, but there will be also data.bp just for this binary data. To view this data, you will need a tool. It's called BPLS, so a list, but with the format BP, right? And you just run it on data BP. Okay, and yeah, let me clean it because I ran it before. Okay, yeah. So and here is my data, right? So here's the type. Here's the name of the variable, and it's how many elements do I have here. And we can view what faces look like. by just typing faces, and then we need to dump it. And we will get our list of faces, right? Yeah. Exactly. So that's the thing about the flatten. You remember the flatten, to flatten the array. We have here 36 entries of lists of size 4. So you have to multiply 36 by 4. Then you will come to the number of points what we have in total, right? And this faces array, as I said, it's flattened. That's why it's larger. And we also have this faces start array here. Right, it shows me where I have to start with reading my face.
Why do you have 7 faces compared to 36?
Good question. it just. Sorry, I didn't hear. Sorry. Somehow acoustics is not good. It just optimization for the loops. If you run a loop, then it's always good idea to have the last entry in the array to be the size of the array. You know, it comes. This one particular comes from Hendrik, so. You can ask him in particular about this one. Yeah, that's it. So yeah, these are the sizes of my lists, right? We also have an owner starts array. Right, so I can show this one. So I have 8 cells, right? This one, it's 8 plus 1. It's 9 cells long. And it just points to me where the owner starts in my face list, right? Okay, so let's run it. Let's run ICOFOAM. So this case is cavity case, but for us it doesn't matter. What did I do wrong here? And now we have some data, and I just will look into the pressure file. Right, so that's a current format in ASCII. We have this non-uniform list scalar, and then we have a list, we have our field. Let's have a look in the how does it look like in Coherent format. So we still have our ASCII information, right? So if we look here into the pressure file, we will see the same picture. our all the dictionary. It looks the same, but always when we have some heavy data, some list, we will have a size here and an identifier into the data.pp. We will come to this. We will come to this in a minute. No problem. And I just wanted to show you actually, if I look into this folder without dpls, right? So what will I see? It's this extension .bp. It's actually, it's not a file per se, it's a folder, right? And this folder contains data 0. So this is my data file. And it's depends how many data files I get. It depends on how many aggregators I will have. So if I aggregate to 8 files, I will have 8 data files, right? And the rest is managing metadata information. And now so same picture here, and I just need to take this one. We need always to dump it, so -d, and then we will see the the values. And yeah, as you can see, these are the same values as here. So it just the same data, but stored in a different form. Sorry. Say it again. I didn't get it. This one is internal, yeah. Well, the boundary we don't have it here in this example. These are 0 gradients, you know. I think the no, internal field is also yeah. Let me look into about VTK, you mean ParaView? It supports the adios format, so there is a adios reader in ParaView, but the OpenFOAM reader, the actual backend to read these files, it's not yet. It needs to be rewritten actually to do this. It may be not as obvious, but we have also another feature. I will show in a second the parallel run. We now have a feature. It's called global uniform. So before, what we have, if you had this uniform entry, every rank would show if the list is uniform. It will just compare all the entries and would put it for its own, right? It won't reduce it globally somehow. It may be uniform on one rank, but it might be non-uniform on the other rank. That how was it before? Now we have this global uniform. So if one field is for all ranks, it's uniform, then we will put it as uniform entry. If it's not, it might be uniform in one rank, but not in another. We will damp it. We will damp all the data to the adios. because otherwise, you know, we have only one ASCII file. Otherwise, we couldn't say this part is uniform, this one is not. Yeah, so it doesn't come for free. But we think it's worth it. So yeah, let me run a parallel case. All right, so I clean it here. Just purpose of clarity. Run block mesh. Decompose bar. And I have four processors here. 4 processor directories. If we look into these processor directories, we will see the same picture as as in the root case, right? We have constant polymesh, we have 0. That is somewhat also beauty of form, that it's the same structure. But we have now some duplication and many files. Let's do the same here. I just clean it as well. Run block mesh and decompose bar. So we still have this one decompose bar, but it's doing exactly what you asked. It's just reordering our mesh such that I have a nice decomposition, right? As you can see here, no processor directories. It's all gone. We write the data exactly into the same place as before. So if I go to constant polymesh, here actually also nothing changed. But if I run bpls on the data, then I see that we have this 2 star. This means 2 time steps. So, or let's say iteration. Because we didn't overwrite the data by now. For debug, we could overwrite, but for debugging, it's better just to put another time step into this adios format, and I just can run it as you can see here. So step 0 comes from block mesh. That was my block mesh execution. I made a mesh. And then I run a decompose bar. This is a different mesh, right? So I reordered it, I dumped it, and we have now a new entry. It's called partition starts. I just show how does it look like, and I have again 4 partitions. 4 plus 1 is 5. So every entry is signalizing me from which cell to start for each partition, right? So for 3rd partition, I need to start with the cell 4. Yeah, the geometric fields. You mean? So the geometric fields will be, if they are written to the disk, to the storage, they will be exactly in the format which correlates to your last mesh, to your decomposed mesh. Yeah, exactly. Sure. So which one you read with this mesh, it will be written as well. Okay. Cool. So now we run decompose bar. Now we can, I run it here as well. We actually don't need to run the ASCII one. I think it's pretty obvious what will happen. I will run it here on the Coherent side. So we have 4 processes, run IcoFOAM, parallel, and I think I have to oversubscribe because I have only two processes here, 2 cores. So it just an API run issue. What's the problem? Wrong directory. Sorry for this. Okay, and we run it. And what we get are the time directories, although we run it in parallel, right? So it looks like a serial one. That's why serial and parallel run are indistinguishable, and also the reason why we call it coherent, right? We also forbid the mixing of the formats. You will see a warning here, or description here why what happens. So let's I think time is almost over. Let's just have a look here. Into the data BP. Yeah, so unfortunately here I don't have any non-uniform boundary fields, but to your question, you would see here an additional entry, right? So it will be, for example, P moving wall value. That's the key part for the this boundary field entry. Let's have a look at let's say P again. Dump it. Okay, so it's again our field. I also can show it in the block structure of this. I think it was large D. Yeah. Now you will see the blocks, and let me check. I didn't check it before. Oh no, it's single data. Okay. No, but so here we have a single file, so it's still written in a single file, but every rank will write, or the agglomeration works like this, that from every proc we will have a single block of data in this file. Yeah, and now to prove the point about the no decompose part, I will just run it with a different number of processes. Let's say 2, and it runs. And decomposition maybe is not as bad, right? Because I decomposed it in 4, and now I just take 2. You see, you know. No. I decompose. No. That's the thing. We don't need to do this. we can read it as it is, as this current format. The run may be not as efficient, you know. The decomposition might be bad. I might have some partition with cells all over the place with a lot of processor boundaries. That might happen, but I can still run it. But the important thing here is that I can read the mesh with as many ranks as I want. I can read it. Then maybe I can decompose it on the fly, right? If I'm already in the solver, to get my nice decomposition. But for reading part, There is from the format itself, there is no problem about this. That's all about the slices, what I showed before. Oh, you're talking about these blocks?
Yeah.
Oh, sorry, it's confusing. These are file system blocks. That doesn't have anything to do with format or OpenFOAM. It's only considering the adios adios internals. Yeah. And sorry. Yeah. Good. I think. Yeah, that's the fun part. We implemented this recently, and I played it with this a bit as well. So we can run with 3 procs. Probably I've never done it before on my machine. I can run it. Okay, I have only 8 cells, so we don't go go. Yeah, restart. You mean restart? Let's do it. So, for example, yeah, now you are very free about your performance utility, your machine capabilities, right? You can run it for night with 32 cores, whatever you have, and then you decide to work along and write it only with 16. So you can do it. It's not a problem. Let's go into system control dict and change the start from latest time. And we can, what number of cores do you wish? 5. Oh, hopefully that doesn't go wrong on this small I need also to change the end time, of course. Sorry, yeah. Up to 2, okay. Yeah, it works. No, but the problem is the decomposition, you know. I don't know how to. Okay, I think we can discuss on this one afterwards. Are there any questions from online participants? Because we need to close the session, I think. Or any questions here in the room? What do you want to write? That's an important question. It's some global list present on each rank. Do you want to agglomerate this? Maybe if you want to write, yeah, that depends. You know, if you want to write on master, just make an off stream and write on master. if you want. Okay. This you're asking about this right function of the. It's for geometric fields. We implement it in the way it's completely the same. So you write, you call right on the geometric field, and it will write the coherent the global array in the coherent format. We have an we plan an interface for this. Yeah. You will get from at your site or from our format, let's say, you will get a UList. It's basically actually a transport layer. So you get a UList locally on every rank. You can fill it up as you want, and then this UList will be written one after another, right? But yeah, okay. The UList is non-owning list, so this data will be already in Adios, right? Adios needs to duplicate it anyway at some point, right? So if you give Adios some data to write, then at some point it may be not the twice as memory, but you will have some data be copied into Adios buffer, because Adios needs to send it to the writing ranks and so on.
And each of them sells maybe this code again at 20 or 100. And all ones by this I can put it, and then yeah, and then that's put it. Because the thing for I just take all to one rank, put it in combination formats, and then write.
No, not this aggregation may be to one rank, but it may be also to several ranks. Yeah. Like if you have thousands cores running, you just take only 20 to write the data.
Really, don't worry. They are talking about number of cores and data that is
okay, we can continue on discussion here. I just close the session, right? Yeah, thank you very much. Thank you.